LHC is designed to have one of these protons bunch every 25 nanoseconds. In the real world, in the real machine, there is not one bunch every 25 nanoseconds because we have some spaces between the bunches. It depends on how many we put into the machine. But this kind of stuff is capable of accelerating things one every 25 nanoseconds. Now, I started saying that this is a microwave oven because the microwave oven is exactly like this. The problem is that we don't want the food to be accelerated. So the first and only difference between the two is that this one, the field inside has to be synchronized with the passage of the particles. Because we have to wait for the particle, then we switch the electrical field, and then we switch it again because there is another particle bunch coming. And this is why the LHC is called a Large Hadron Collider. But the machine before the LHC and the one before, they are called PS, that stands for Proton Synchrotron. And the other is SPS, Super PS. It's synchrotron because protons has to be synchronized with the electrical field inside. And this is the only difference between this and the microwave oven. Because in the microwave oven, we have the radio frequency that is not synchronized with anything, and so all the particles inside are accelerating and decelerating randomly. So you are making them vibrate and not accelerate in the sense of the particle acceleration. So this is the difference. In that case, we are not accelerating anything because we are making molecules, water molecules in particular, vibrate. While here we are synchronized with the particle, the passage of the particles, and we are pushing them. This happens only in one spot in the 27 kilometers. It's not one of these. You can see here several of these. It's three per every pipe of like this, but we have several pipes of this. But the point is that we have 100 meters where we accelerate particles. The rest of the ring, it's just because we want them to come back and we accelerate again. Of course, we have one of these for the particle that's going clockwise, let's say, and then we have another one because the LHC is Large Hadron Collider. So we need one beam going in one direction and the other beam going in the other direction if we want them to collide. Now, this is to accelerate particles, but we have to find a way to make them come back, so to create the ring. And this is the device.
So it's basically two rings, one for clockwise and one for counterclockwise.
More or less.
Which is
You have two pipes in one ring. So yes, you have more or less one ring. The point is that in 4 places in the LHC, you can have collision. So the beam are crossing. And when the outside beam is crossing with the inside beam, they are switching. So you have, it's not that you have 2 rings, separate rings, but you have one ring that is outside and sometimes it's going inside. That's why this one is the most common place inside the LHC. It's called dipole magnet. It uses the magnetic field to bend the trajectory of the particle. Now, I really hope that every one of you knows the Lorentz force. But just to recap quickly, there is a beautiful way to be like a proton. So if we have inside here, we will have magnetic field that can go up or down, depends. Now, let's suppose that it's up, like my hand. If I'm moving with this speed, with this direction, the force that I will feel is along my tongue. So I will go counterclockwise. If the field is opposite direction, I will go clockwise. This is a quick way to explain to the students that are not engineers. Anyway, we want to create this magnetic field inside to bend the trajectory to keep them in a circular path. Now, not all the LHC, like I said, this is the most common piece inside the LHC. But not all the LHC is made by this, because of course we need the radio frequency accelerator. Then we need something to understand what happened after the collision, because otherwise there is no reason to do the collision if we don't. And then we have another kind of magnet that we will see later, that is the polar dipole. But anyway, if you picture the LHC from very far, it's a ring. But if you look very close, inside here you have a turning radius. But outside this machine, everywhere, but not inside, particles are going in a straight line, because there is no magnetic field to bend the plate. Anyway, all we need is a magnetic field. And if you want to create a magnetic field, you take a nail, you take a wire of copper, you turn the wire a lot of times, and then you connect to the battery. You have your magnetic field. And here we have the same, it's just much more powerful. We have the nail, it's a strange shape, but it's a nail, because basically it's iron. And it's pointing here. And this, the reason of the iron here, is because we want to push the magnetic field where we want it. And here you can see that it's taking the magnetic field from all the part and is pushing it in the middle of the beam pipe. Because in the middle of the beam pipe is where we need it. Now, you are engineers, I'm a physicist, so you know efficiency better than me. If we want a lot of magnetic field at the middle of the pipe, we want to make sure that everywhere else there is no magnetic field. That's why we are focusing it like this, because we want the magnetic field only inside. Then we need the wire, and this is the wire. It's going like this, around the nail. So it's going back and forth, back and forth. Now this one, unfortunately, these are two rays, these yellow rays here. They are ready to host one of these. There is no one today, unfortunately. But you can imagine that this is more or less the length of the ray. So this is just one small piece of it. And what the difference is that this one is going for the full length. So here this is the end of the magnetic dipole. Now, something interesting is that inside, and unfortunately we cannot see, we have the particle beam that is passing through. Now, you can say to me that when a beam of particles, and we are talking about 1 billion, 10 to the 11, it's actually 100 billion of protons, it's a lot of charge that is moving basically at the speed of light. And for all the purposes that are not related to the particle physics, is moving at the speed of light. So if we want to simulate the beam, the frequency of the tuning of the cavity and whatever is done considering that they are moving at the speed of light. Now, if you have a lot of charge that is moving at the speed of light, you will have a lot of current induced in the pipe. Now, this is stainless steel, and stainless steel is not very good conductor. So it means that if you do like this, like it is now, it will melt very soon, because you will induce a lot of current inside the pipe, and you will produce a lot of heat. That first of all, this heat is power subtracted by B, so you are losing energy instead of gaining energy. But still, the steel is not capable of maybe of resisting to this power. Anyway, what we do is to put something that you can see inside, but unfortunately it's not possible to do. We have a copper protection, let's see. So what the beam is seeing is just copper that is way better to dissipate electrical energy. But the problem with copper, it is not as stiff as the steel. So we have the steel because we want to sustain a lot of pressure, because we don't want any molecule inside. So we have a very good vacuum inside. And for this we need the steel to sustain the pressure. Then we have the copper, because we want to dissipate the imaginary current that is produced by the passage of the beam. I'm telling this to you because this is basically a very simple, an extremely simple machine from the point of view of the principle of working. But from the point of view of doing this, it's a mess, because you have to consider a lot of stuff. Now, let's go to the quadrupole.
So yes, this is the copper shield is actually doing the focusing of the beam?
No, this is So if you have questions, just interrupt me and shoot the question. This is the same basically. The only difference is that we don't have just 2 coils per pipe, but we have 4 of them. Indeed, that was called dipole because we have 2 coils, and this is called quadrupole because we have 4 coils. And if you look inside, this is made by 6 coils, and it's called sextupole. Now, this and the dipole from the outside look exactly the same. That's why now you cannot see it here because we are not testing a quadrupole here, but the quadrupole are a different color with respect to the dipole. But from the outside they look the same. It's just that inside you don't have 2 wires, but you have 4 of them. The point of this is that you don't have a uniform magnetic field inside. It's always constant magnetic field because this is a magnet, so it's not moving the magnetic field. But inside is not it's not constant magnetic field. What you have, it's a shape like this. So you have a north pole here, a south pole here, north, south, or the opposite. You can have south, north, south, north. And what it's doing is that you have no magnetic field inside because it's symmetrical. So in the middle you don't have any magnetic field. While the magnetic field is increasing while you are going farther from the center. The point is that particles that are far from the center will be pushed toward the center, while particles that are in the center will feel no force. What we are doing is to focus the beam. The point is that this kind of, for the magnetic law of physics, and there's nothing that we can do, we can focus the beam horizontally or vertically. There is no way to focus it like with a lens for light. So what we do is to use one of these to focus the beam like this, and we stretch it like this, and then the next one we will be used to stretch it vertically. The point is that you cannot stretch it without changing the surface, because if you imagine a lot of spaghetti, now I'm Italian, of course I do, I talk about spaghetti, but anyway, if you take spaghetti and you do like this, they will spread, and it's the same for the protons. If you push them inside, you're moving the vector of their velocity, and so they will spread sooner or later. That's the limit of this thing. You cannot put just one and wait because the beam is focused. Because the beam is focused when you are inside, but sooner or later, and it happens very soon, they will be again defocused. So you will have one for focusing on horizontal, the other that is focusing in vertical, but of course when you focus you will have a spreading of the velocity. And so soon you will need another tool. Using this and this, by the way, the sextupole is more or less the same, but it's not doing this, it's said that it's removing the chromaticity. So if there is some proton that is going faster, the energy is different. And if the energy of the light is different, you have a different color. That's why it's called chromaticity. You can use this to reduce the energy of the one that has more energy, and increase a little bit the energy of the one that has less energy. But this is a piece that is very rare in the LHC, and in particular Accelerator in general, because it's needed if you want to make very precise bunches of protons. Anyway, in the LHC, like in all the other accelerators, there is dipole, quadrupole, quadrupole in such a way organized in a scheme that is repeated for all the ring. Now, this scheme is called the optics. So, who decide the current, the intensity of the magnetic field, the position of this, is who deals with the optics. And yet, of course, there are a lot of controls, whatever, but this is something that is fundamental for the machine to work. Because if you have just the current inside one that is wrong, you will have no beam, because it's not one turn. In the LHC, there are 11, 24, 245 turns every second. So it means that if you are wrong of 1 millimeter, in 1 second, this 1 millimeter will be 11,000 millimeters, because it's 11,000 turns per second. So we have to be very careful turning this current inside one. Now, I said that if you want a magnetic field, you need a nail and a copper wire. The problem with the copper wire is that if you want to increase the current, in principle you can, but in reality, the electrical current inside the copper wire will melt the copper wire, because the copper wire has a resistance. So what we use is something that has no resistance. Now, if we, in principle, we don't consider the resistance, so we neglect for the first moment the resistance of the copper, and we say that we design a magnet like that, the current that we need to have the magnetic field that we need is 30,000 amps, roughly. Now, maybe you don't need an example to understand how much is 30,000 amps, but I will do it anyway. So the electrical plug in houses, it's rated maximum to 15 amps. So it means that you need one wire that is 1,000 times bigger than the wire that is going into the room. This is the point. And the point is that this wire is this one. And you can imagine that more or less is, now, the wire of the plug, let's say that is 1 millimeters. If we want one wire that is 1,000 bigger, 1,000 times bigger, it means on the surface. So it means that is 30 times bigger here, and more or less we are there. Now I'm not sure it's linear, but anyway, this is rated for 50,000 amps, more or less 30,000. Now, you can imagine that this is not something easy to use, and of course, if you want to do this, then you have to make the coil. So this is one. This is the plug that you have, but then you have inside you need the coil. No way we can do it. And then of course this is heating up. So we need something to cool it. Because if we don't cool it, sooner or later it will melt. That's why instead of this, we are using this. And this is not copper. You can play with it. This is not copper, it's called niobium titanium, and it's a superconductor. Now, superconductor, it means that it has zero resistance. It's not small resistance. It's just like copper. It's just a different color. But if you play with it, it's a wire. It's nothing special. And this is the reason why it was chosen. Because it's nothing special when it's a metal, it's just like that. The point is that in some condition, in the correct condition, the resistance of this wire is zero. And I'm not talking about very, very small, like 1 ohm per 1 kilometer, no, it's zero. I mean, yes, we have nothing. Now, it's not 0.0000000. I don't know how much zero there are before the 1, but there is a 1, because the point is that we are not able to create niobium titanium 100% pure. So the pieces of external thing are creating some resistance. So it's not really zero, but it's very, very close to zero compared to any other conductor. That's why it's called superconductor. Now, the problem is that we have to cool it down. It's not the same as the copper, because with the copper we are wasting energy to heat it up, because there is resistance, and then we have to cool it down. In this case, we are not heating up, we are just cooling it down. So the environment is heating up, and it's staying at the temperature that we put it. But the problem is that this can be cooled at minus 20 degrees. This has to be cooled at minus 270 degrees. Now it's working at 1.8 Kelvin. It's very, very cold. The point is that this, in principle, would work also at 20 Kelvin. It's not hot, but I mean it's hotter than the 1.8. The point is that when you put this inside the magnetic field will interfere a little bit with the superconductivity. So if you want to put this inside the magnetic field, you have to lower a little bit the temperature of the working temperature. We are using this to create a magnetic field, so of course we will have magnetic field. And this is a very complicated phenomenon. And the point is that every time we go into the quantum mechanics field, there is nothing that is easy to explain. It's easy to make picture of it. So now I can explain why electrons here are working together with there is zero resistance, but still it's a picture, it's not the real thing. Now the point is that inside any conductor there is the conductor that is like there is the lattice of the conductor, and there are electrons that are moving inside. Now, every electron is moving by itself. So every electron can touch the lattice, can touch the other electrons, can touch everything that is external to the lattice of the metal of the conductor. If we create something like a wave that is making the electrons move all together, and if we are able to sustain this wave for all the conductor, we have a superconductor, because now the electrons are dancing all together. But this connection is thanks to the quantum mechanics. It's very the energy of this connection is very low. So if we want to sustain it, we need that the thermal energy from outside is lower than this energy. And so that's why we have to cool it down. Because if we are at room temperature, this energy is too low. And so they link together, but this link is broken as soon as it's full. And that's why we have to cool it. Now, in copper, it's not possible. Even if you cool it down to 1.8 Kelvin, it's not happening. The temperature of the working temperature of these superconductors, it depends on the characteristics of the material. There are some superconductors that are called high temperature superconductor. Now, high temperature does not mean high temperature. It means that it's higher than the liquid nitrogen, because liquid nitrogen is very easy to buy. I mean, they told me that it's like 20 cents per liter. It's less than gasoline, so it's very cheap. And it's liquid at a temperature of 80 Kelvin. So as soon as we have a superconductor that is working at 81 Kelvin, it's easy to use, in the sense that we pour some liquid nitrogen and it's working. The question is, if this material are existing, why we are using niobium titanium that is working at 1.8 Kelvin? The problem is that, as I said, this looks like a metal. So if we want to wire something that is 27 kilometers long, and then we want to create coils of this, so it means that we need a lot of wire we need something that is easy to use. Because, for instance, the first superconductor ever discovered in 1906, 1908, I think, beginning of 20th century, it was on mercury. But of course we cannot use mercury to build the LHC, because we create something that is working very good at 1.8 Kelvin, but then when we want to transport it, it's mercury, so it's not pleasant. There are also, like I said, the superconductive, high temperature superconductor, but these materials are ceramics, so they are very brittle. If it's possible, it's better to avoid them. And then there is one other reason why we want to use this. Because you can imagine, if we want to cool down something, now, you for sure know how to, the hardest thing, one of the hardest things is to cool one chip when it's powered. Because otherwise you go to, the Intel found it the hard way. Because they were going to 4 gigahertz, 5 gigahertz, yes, no, it's not possible, because you cannot dissipate efficiently the heat. What they are doing, the best that they can do, is to flow some liquid inside the chip, and then remove the heat somewhere else where you have big room for heat dissipation. We are doing the same. There is one liquid that is flowing in 27 kilometers, and there is one place where we are cooling down this liquid. First point, it's not easy to find something that is liquid at 1.8 Kelvin. And we have two choices. One is hydrogen, and the other is helium. Now we have something that is very cool, very cool. Then we have something that is liquid, but it does not want to be liquid, because the hydrogen and the helium are gas. So one gas, when something is gaseous, it's 1,000 times bigger than something liquid. So they don't want to be inside the pipe. And then you have something that can explode, because the hydrogen can explode. So we want to avoid the use of hydrogen. And then there is another thing. If you imagine that you want to push some water, let's say, for 27 kilometers, you try to imagine the size of the pipe. Very big. Or you need a very good pressure. So there are two cases. Or you have low pressure, high intensity, so big pipe. Or you have small pipe, but huge pressure. So it means that the pipe will have very thick walls. Now I will show you the pipe. Now, the pipe is this one. It's not a pressure, because you see, you can touch it. It's very, very thin. So the point is that, as I said before, when we are at 1.8 Kelvin, we are not in the regime of the classical physics, we are in the regime of quantum physics. And as for the superconductor, there is a trick also for the cooling. Because in this case, we are using helium, that when it's cooled below 4 Kelvin, it becomes superfluid. So it means that we have this liquid that does not need high pressure, because it's flowing everywhere. And I strongly suggest you to go on YouTube and to find, search for superfluid helium, something like that. And it's, when they discover it because they put some helium inside the cup, they cooled it down, and then there was no helium anymore. Because the helium was so super fluid that was leaking through the molecules of the cup. And it's very hard to keep it, it's impossible, because the helium is a very small molecule, and it's flowing without resistance. So it's really complicated.
So how does it stay in the pipe? And
because the pipe is done on purpose. So it's not that it's not possible. It's just that if you take another kind of material there, I think that's copper beryllium, but I'm not 100% sure. But I know that if you take a metal, it's staying. But it's not usually when you want to study something, you don't use a metal because metal reacts with something. I don't know why. But when they discovered it, they were not using metal. They were using some ceramic, and so it was not really pouring towards the molecules, but towards the micro structure of the thing. But anyway, in this case, you have one very small pipe, and that is not thick, because you are not using a lot of pressure to push it for 27 kilometers. And this is another enormous advantage of this.
It's very small, so you have very small volume. So how do you cool down this very small volume?
Because you don't have small volume, because the volume is the speed times the. If you don't have, you have a very low section, but still you have no resistance, so you can increase the flow as you want.
What's the speed of the liquid?
I have no idea, but it's not
slow.
The point is that here you want to do something. It is outside as the tunnel, and if you have a cave, you know that inside everything that is deep at 100 meters, 50 meters below the ground, it's more or less 15 degrees, 15, 16, 17, 18, but it's the temperature of the air. So it does not depend on how much cooling you have inside. You will have 15 degrees. So if you have a cave, it's hard to heat it up to not freeze inside. In our case, no way we can cool it all the time, and then it's not comfortable because people have to go inside. So also because of that. But anyway, here inside the tunnel we have 15 degrees, let's say. Inside we have 300 degrees less. So here there are minus 270 degrees, basically, two caveats. Of course, there are the usual three methods to avoid thermal contact. First of all, there is no contact. No contact, it means that it is as low as possible. Then, inside here there is vacuum. So the air cannot transfer the heat. And then we have this that is mirrored. Of course, this is mirrored for the infrared light, because the heat that we want to keep outside is transferred using infrared radiation. Now, inside here still we have this that is what is cooling, but this is the passage between one and the next. So we want to avoid to lose thermal energy inside here, because this is the connection. So that's why this is very small here, because we don't want the heat to go away, and the heat is going through the surface of the pipe. When we go inside, and we can have a look when we are going back, the pipe is bigger. Maybe some of you remember that when there were 3 pipes, and I didn't mention nothing about the first pipe. It was important. But that pipe is bigger, because when you are inside, you don't want to avoid the heat transfer. You want to stimulate the heat transfer. So the biggest the surface, the better it is. Of course, if you have a huge surface, you have a big volume inside, and so you need a huge flow. So everything is an engineering compromise between what we have and what we don't have. Anyway, I think that for sure CERN is one of the biggest consumer of helium, but I think that we are consuming 1/3 of the annual production of helium. Because as I said, helium is not easy to keep inside something. So when you flow it, you need a lot of it, because you are leaking it everywhere, and also because you have 27 kilometers of pipe that even if it's small, it's still 27 kilometers that you have to fill it, because you don't need high pressure, but still you need the helium to fill it. It's a liquid, so if it expands, it becomes gaseous, and it's not anymore at that temperature. Anyway, I can show you because the same problem that we had before, that the beam is passing and is creating, is inducing currents, we have also here where we are connecting two pipes. And in this case, it's even worse, because you can see, of course, you can imagine that it's not easy to align with vacuum-tight precision two monsters like this. So we have these pedals that ensure the quality of the vacuum inside. The point is that when we are inside the beam pipe, the current induced by the beam has to go like this straight. But inside the steel, that is not good. But in this case, the steel is very thin, and then the current has to go like this. So the heat produced here is huge, and the interaction of this induced current with the beam, it's huge. So what we do is this kind of stuff. So it's basically something that can move, like the bellow, but it's copper. And it's not sustaining any pressure, because it's in vacuum, everything is in vacuum. So this is more brittle than this, but still there is no pressure on it. There is this is a better conductor, not a superconductor, it's useless than a superconductor, but it's a better conductor, and this is a worse conductor, but it's outside. Now, there are some devices that are moving, but this of course is not moving, because when you place it, it's staying. So you have this, okay, you create some dust, but the dust is falling and it's staying there. But there are some other devices that have to be moved while the LHC is in operation. And so in that case, you cannot use something like it, because you can imagine that when you are scratching this, to our eyes is nothing is happening, but some molecules, some pieces, I mean, it's wrong to talk about molecules in copper, but anyway, some pieces of copper can fall, and if a piece of copper that is invisible to the eye, but it's also 1, 2, 3 atoms of copper is falling, for the beam is a collision. And if you have a collision inside, it means that the beam is not staying anymore in the pipe, because of course when you have a collision, it's changing direction. And then you are producing debris, let's say, so particles that are scattered, that are going inside something that you want to keep cool, and it's not cool. So I mean, it's copper, but if you want to...
So, actually, I didn't understand what's going through this one.
The current that is induced by the passage of the beam.
Alright,
So you have the beam in the middle.
beam is inside.
It's in the middle, yes.
Okay. And why those small pieces?
Because you have to let it move when you want to align this. So when you are
so
mounting
it's just when
it,
you're mounting it.
yes,
Okay, but
it's moving.
afterward it's not moving anymore.
Exactly.
They have to maintain the electrical contact with this casing as well? So
Yes, the
current has to
contact. So the
be able to
contact
flow
is
through,
between
right?
the first one and the second one. You have to have the better possible electrical contact. Now this is not the best possible. You see, 1 or 2 are any contact, because this is for the purpose of the visit. Of course, we cannot play with the real one, but the real one. And in this case, there are also others that are from the outside, like this.
Oh.
And there is a wire here, but I can tell you, because you are engineers, so you can understand that these small pieces, that is something that you say, okay, very easy. It's complicated, and we had the problem in the previous, let's say the not updated version, because one like this was with a ring here, the ring broke, and so there was no contact, and this was heating up. And of course, when it's heating, you have some gas that are, let's say, imprisoned inside the copper. Even now, I'm touching it. My things from my, I don't know, grass or something is here, is depositing. So when I heat it up, it's evaporating. And if something evaporates inside a vacuum pipe, you have no vacuum anymore. So this is one example of how complex is a machine. Then if you neglect an effect on these stupid things that is so easy, so you create a mess.
is it possible to clean the pipe if it's contact with it?
Now, there are there are a few. It's not too clean. So it's not an easy question. First of all, they clean it, of course. There are vacuum grade. There are some companies that can clean it. There are some places at CERN that can clean it, but still it's a chemical cleaning. But what they do is something called bake out. So basically, they put some heating stuff outside, and they heat it up for at 400 degrees, and they keep it for 2 weeks. So if everything is inside, it's burning. It's like the catalytic converter in the car. When you do a very good accelerator, you have a lot of smoke behind, because you are burning everything that was inside because of the high temperature. This is the same. We are doing more or less the same, but sometimes it's not enough. But the cleaning in this period of time of the LHC is very critical, because we had a lot of problems due to the helium that was not 100% helium. Because if you have something, when you cool that liquid at 2 Kelvin, that something will become solid. So if you have something that is flowing inside the liquid when you are filtering it, when it's cooled, you cannot filter it anymore, and it will clog everything. We have this problem for a few minutes. Now the problem seems to be solved, because they were cleaning the helium. But once again, this is another example that everything you say, okay, come on, but what the helium is pure to 99.9999%. No, it's that 0.0001 that is making mess for you.
This is basically to move when it's placed. It's not stable.
Well, they put it with a precision of tens of millimeters, I think, but still it's not enough for the vacuum type.
Afterwards, this is solid. When it is in place.
Yes. Also this one.
How do you cope with like Earth moving?
Also because of this. Now the LHC is so sensible that we can see the tidal effect of the moon on the Gini plate. Because when the moon when there is the tidal, I think it's in English. When you have the tide on the other side of Gini plate, the LHC is going up because it's lighter, and then it's going down. And also from an electrical point of view, it's very sensible. I know, because I'm trying to develop amplifier for a detector that is very close to the pipe. They are very sensible to noise, because they were losing the beam. They saw noise inside the beam when the TGV was passing. So this is the complication of the LHC. It's a very simple machine. I can explain how it works in 1 hour. More or less, these are the components. So the idea, it's simple, but when you go there and you try to do it, it's a mess. You have hundreds of columns that it was not possible to foresee, to foresaw that, sorry, every time, sometimes I have to. Anyway, it's not possible to foresee all the problems that you have. And the last example is this one. This is the superconducting wire that you have to solder. The problem is that you cannot solder that material, and so what they did is to use some copper fluids outside just to keep the wire touching. Now, this copper thing was not enough for a few joints, particularly one joint. And what happened when this is something that is working for every superconductor? When you have a piece of something, let's say in this case it was some air, between the two, you have something that is not superconducting. So when the current is flowing, you have a resistance. That resistance is not a problem, because you have a big resistor in parallel with a small resistor. So in principle it's not a problem. But when you have a huge current, a small fraction of a huge current is a huge current. So you have a huge current flowing through that something that has a resistance. It means that it's heating up. But when you heat up, you have the problem that we wanted to avoid using superconductors. So you have some heat generated inside the superconductor. So here, just to be 100% sure, here you have the heat, but you have it outside. In that case, you have the heat inside what you want to cool. So it's much more complicated to cool it down. And in this case, it's something that happens so fast that it's melting before you can even realize. In a few microseconds, everything is not working anymore. The superconductor is so it's not superconducting anymore, and it's an exponential growth of the resistance. And this is what happened. And when this is melting, of course, it's not melting back by its own, because you have 30,000 amps that arrives, and they found no more place to go. So what happened is that if a little bit of current touches the helium pipe, you have once again something that wants to be gaseous. And so you have something that from that small volume becomes 1,000 times bigger. And this happened the first time that they turned on the LHC. Maybe you remember that it was on the news. Yeah, because they were happy, okay, the machine is on, so it's not working. They thought about the helium leak, because the helium is easy to leak, so they thought about it. But then they went in the tunnel and they saw that 4 or 5 of these were detached from the floor because everything was exploding. There are valves because of course the helium was locked, but the pressure was not was too high, and a few of these valves were broken. So it was a mess. And they stayed. I was not here. I arrived the next year, the year following. But they did not solve the problem. They said, okay, this problem will arise only when we are using current bigger than this amount. Indeed, the design energy of the LHC was 14 kV, while they were using 6 kV, 6.5 in the end. Now they solved the problem because they put like this here. They put 2 screws, 2, 3, I don't know, some screws. So the copper belt cannot be removed by heat or by something. By the way, this was not a flaw in the design, because the design was good. It was the soldering guy that was not doing his job 100%. But you know that if you want to make sure that everything happens, you have to foresee 3 times the problem that you have. So you are fine. And just another complication if everything is not enough. Of course, this is now at room temperature. When it's cooling down, it will shrink. And it will shrink not of a negligible amount of material. That's why, also because of this we have problems. Because yes, it's not moving during the operation. It's very slow movement due to the cooling that is done like twice per year. It takes 1 week to cool everything down. Then you have earthquakes. This is not a region where you have.
No, but maybe very small
Very
ones.
small ones, yes, you can have them. You can have
Or feel the big ones that are far away.
Yes, yes. But this is not something normal during the operation. That's why you can use this, because you have an earthquake, you stop the machine, and then the dust of copper is falling, and then you start the machine. I mean, it's not a huge efficiency problem of the machine. Okay, now we can move on. So we go. No, this is not for visitors.
Yeah.
But there are a lot of other places. We are not going outside. We are going. It's busy, so we stay here. So before I was talking about few rings that are before the LHC. This is the scheme. Now in the other room it's drawn on the floor, so it's just a little bit funny. But anyway, we have, in this case, we have protons or heavy ions that are starting from this that is called LINAC. That stands for linear accelerator. Because as I said, if you want to accelerate something, there's no need to introduce the steering wheel. You just need the engine and wheels without steering. That's why the first track is linear. Then you say, okay, we don't have enough room, so we introduce the steering wheel to have a circular track. In this case, we go from the LINAC, we go to the booster, which is small, 160 meters of circumference. Then you go to the PS, that is proton synchrotron. Then you go to the SPS, then you go to the LHC.
When the protons go to the booster, it does only one turn or several in the booster?
No, it does several. One is impossible to do.
And how do you decide that, okay, it's up to speed, we can switch
Because,
the button and
because there is okay, so when you have a magnet, in theory you can increase the current from 0 to whatever you want. There is a limit to the maximum current, and this is okay, but you cannot control the current so precisely to a huge range of current.
Okay.
So there is also minimum current that you have. So it means that there is a minimum energy of the protons to enter the string without smashing with that magnetic field. So the magnetic field has a radius per every energy. If you increase the energy, you have to increase the currents inside the magnet to have exactly the magnetic field to keep them in exactly that circumference. If you reduce the energy because you are starting, if you have low energy, you need to have a very low current. But it's not possible to do it because you cannot control the current to that wide range of values. And so you are using this when you have enough energy to go into the next.
the minimum requirement.
Yes, you go in the next.
And how do you do the transition from one to the other?
There is another magnet that is called kicker because it's not working always. It's working just one fraction of a second. When the beam is there, you kick it. Poof. And
Nice.
so there is, well, actually here it's just a scheme, but there you see the path of the proton. So you have one that is entering, you have this, then they go here, and they go here, then they go here, and then, and this is the tricky part. From the SPS to the LHC there are two pipes, because there is one that is doing like this, and the other that is doing like this. Because if you look at the arrow here, every other accelerator apart from the LHC has particles going only on one side, on one way, because the LHC is a collider. So it's the only one that needs to. And before the LHC, as I said, this was not built everything for the LHC. They were using this, then they said, okay, the energy is not enough, let's build another one. And that's why the energy are fine between them. So the maximum energy of this is compatible with the minimum energy for the PS. Because they build this and then they say, okay, it's not enough energy, let's go for the PS.
But
Actually, this was
so those before were also colliders, but now they are not colliders anymore.
They were not colliders, they were accelerating particles and they were shooting to a target. Indeed, you see here, this is a target, this is target, this black is a target. Because if you want to have a particle collision, there's no need to make two beams.
It's
Just
twice
one.
the power.
The point is not twice, it's even more, because when you collide two things that have the same momentum, the center of mass is steady. So the speed of the center of mass, when you have a central, very good collision, is zero. While in that case, you cannot have zero, because you have something stopped. If you do the math, you see. But also, you can imagine that if you are shooting at something, you will have debris that are moving all together. So the center of mass of the system is still moving. And in our case, what we want to do is not to produce kinetic energy, but we want to produce, let's say, potential energy that will be converted into mass. So we are producing, our goal is to produce new particles. So we want to waste as little as possible energy for the kinetic energy. So if you have a central collider like this, like the LHC, you are very efficient, because when you have a central collision, that is not the case, because of course you can imagine that not always the collision is perfectly aligned. You have that 100% of your kinetic energy becomes available for production of particles. Now the other thing is that the LHC, here it's PS, super PS, so both machines are synchrotron because of the acceleration technique. The LHC is also a synchrotron, but we prefer to call it accumulation ring, because we can imagine that, okay, it's the highest energy of the particle accelerator in the world, and it's something, but it's also the highest luminosity. So luminosity, it means how many collisions we can have every time beam are crossing. And this is also the biggest, the huge amount of collision, because it's an accumulation ring. So what does it mean? It's like a train with empty cars. The train is accelerating, it's going around, but then you can fill one car at a time. So the SPS is feeding the LHC, not all together. So we can accelerate in this everything, all the rest apart from the LHC. We can accelerate a certain amount of protons that is limited. But when we go to the LHC, we can put this amount, and then we wait that another bunch of protons is ready, and then we put it into the LHC. Then we prepare another one, and then we put it into the LHC. That's why it's called accumulation ring, because we accumulate a lot of protons inside, much more than available in the SPS, and then we start accelerating the train, and then we start colliding the two trains.
How long does it take to set up an entire?
Well, in this moment, a lot. 2 hours, I think. But when they were at regime last 2 years ago, with the pre-updated version of the LHC, it took half an hour. It depends, because you have a lot of parameters. If you have them under control, you can go quickly. For instance, now we had a problem, but it's not just it's not that it's difficult. It's a lot of details that has to be taken into consideration. Now, for instance, every time we put the beam was rising in energy, we had the vacuum issue inside the machine. So the vacuum inside the machine was increasing. Okay, so we cannot increase the energy as fast as we want. We need to control the vacuum, for instance. Then when this problem is under control, we can increase the ramping speed and whatever. So basically, we have beam for 1 week. So when we went at regime, there was beam going for 1 week. So it means that for 1 week we have collisions. Yes. You have 1 week of collision, then you have 1 hour, 2 hours, when you remove the beam and you put another beam.
So every time you do the collision, say Atlas or CMS, right? Basically just they want to set up the collision.
And they start clean.
And you start over.
Of course, when the beam is not colliding, Atlas, CMS are standby. So there is no reason to stay. I mean, there are reasons, for instance, to align or something, but they are not making physics. They will not discover a particle if there is no beam.
It's just like basically it's like a one shot.